So today we're going to talk about 3.2, derivatives of logarithmic functions or derivatives of logs. And the important thing to remember here is all of the derivatives and the techniques for integration that we've already used are still going to be applicable. And the only difference is we need to remember all of our log properties and the standard definition for the derivative of a log. And so you'll see in the blue box on the left side that the derivative for logs is written here. And then the second thing you're going to notice is with log base b, typically in calc, you're going to see right here, we use natural log or log base e. Okay, those tend to be the easiest, and that tends to be a majority of what we use. Okay, so what we're going to do is just practice a couple of different examples of finding the derivative of a log, and then we'll get you started on your problem set. Okay. So the first example that we're going to talk about is just a diagram that shows the derivative of natural log. And so you'll see the blue curve for the derivative of the natural log. And then you're seeing at some points there at 1/2, 1, 3, 5. When x equals those values, you've got the red tangent lines drawn. And one of the things that you should notice is that the steepness of the tangent lines, the steepness of these lines is decreasing. Okay, and so the question at, for example, on B, it says the graph of y equals natural log of x have any horizontal tangent lines, and use the derivative of natural log to justify your answer. And so keeping in mind that you just wrote down the derivative for the natural log of x is 1 over x. And so to answer the question, does the natural log of x have any horizontal tangent lines, think about what we know about fractions. Is this ever going to be equal to 0? And what we should remember is that for fractions, in order for it to be 0, the numerator has to be equal to 0. Since 1 will never be equal to 0, the answer to B is no. And the reason is the numerator is never going to be 0 in this case. Okay, so the y equals natural log of x does not have any horizontal tangents, and the reason is the numerator will never be 0. Okay, so example 2, find the derivative of the natural log of x squared plus 1. Okay, so what we're going to do here is we're actually going to apply the chain rule as well as the new rule for the natural log. So let me remind you, I'm going to have my little thinking bubble. If this is our function, then y prime is going to be 1 over that thing times the derivative of that thing. Okay, that's applying the chain rule. So when we put this here, we need to remember that the basic rule says, oh, that's 1 over x. But that's implying that what's inside the parentheses right here is just x. However, when it's a function u or p or q, whatever you want to call it, it's going to be 1 over that thing times the derivative of that thing. So in this case, we're going to say y equals the natural log of x squared plus 1. So when we take y prime, it's going to be 1 over x squared plus 1 times the derivative of that thing. Okay, and this is because of the chain rule. So my final answer, I'm going to finish on the next line. It's going to be 1 over x squared plus 1 times the derivative of that, which is 2x. So my final answer is 2x over x squared plus 1. Okay, that's y prime. Or in this case, the derivative of the natural log of x squared plus 1. Okay. Next example is actually worked out for you. I'm going to talk you through it, and I'm going to show you how we use this. And so there's a couple of things. The example worked out here does not break it down very well, so I'm going to break it down for you. Remember that log properties say that if you have a quotient, I'm going to use symbols here, a box over a circle, that you can break that down to the natural log of the thing that's on top minus the natural log of the thing that's on the bottom, right? So for logs, and natural log doesn't matter, but logs in general, when you have a quotient, that quotient can be simplified to a subtraction. Okay, now over here on the side, a couple more log properties. If you had the natural log of, I don't know, something times something, that can be broken down to the sum of those two quantities. And then the other one that you might remember that it should be familiar, when you had some exponent, you could bring the exponent down in front and take the exponent times that. And so up here, I want to point out that you have a quotient, and that quotient is going to lead to this minus sign. The second thing you should see is that you have this product, and that product leads to the plus sign. And the third thing, you have an exponent, which leads to an exponent. Keep in mind also that here, the square root is actually an exponent. Okay? So once you have it broken down into log properties, and you've simplified it in that form, the derivative taking is so much easier because now you just have the sum and difference of items. So here you have 2 natural log of x becomes a constant times 1 over x, which is the derivative of the natural log of x. The second thing you have here, the natural log of sine x. It becomes 1 over sine x times the derivative of sine, which is cosine, using the chain rule. And we want to simplify that to cotangent x. And then last but not least, you have 1/2 times. So again, you have a constant times something. So the constant becomes 1/2. It just stays, right? And so you have your 1/2. And we're distributing that, so I'll erase that. So you have the 1/2 times the quantity, 1 over x, times the derivative of 1 plus x, not 1 over x, 1 plus x. And the derivative of this is just 1. Okay, so that's why you don't see that here. In my class, I don't care if you distribute the 2. That is irrelevant. Okay, so you could have left that, and that's okay. So here's your final answer. Okay. Again, the first thing you do before you take derivatives is use your log properties from pre-calc. Next example. Again, worked out for you. But when we have the absolute value, they're just telling you that the sine x has to be positive. And again, I cannot stress this enough. This is because natural log, by definition, x has to be greater than 0. Okay, we know that the sine value can go between -1 and 1. And so in order to do this, we have to set these absolute value signs here because we're saying we only want the positive values for the sine of x. Okay? And notice here, we have the chain rule. 1 over that thing times the derivative of that thing. And that's how we get the 1 over sine x times the derivative of sine x. And the derivative of sine x is cosine x. Okay? So the chain rule is just to guarantee that everything that's changing shows that it has a change. Remember, derivative is rate of change. Okay, so now we want to do an example, and this is using logarithmic differentiation. And one of the things that will do for us is help us revisit the idea of 3.1, implicit differentiation. And the other thing it does is it helps us simplify the derivative taking process. Okay? So you can do this one either way, and according to the instructions here, I'm going to use logarithmic differentiation. And the way that starts is by taking the natural log of both sides. And I'm going to switch a few things while I'm here, because I like using my power rule, and then I have it written like that so I don't forget it. So all I did was convert this cube root to a 1/3. Okay, so now once I have it written as that, I'm going to use log properties to simplify the the right-hand side. So the natural log of y is equal to the natural log, and I'm going to do it in 2 steps. It's that minus the natural log Oh, my bad. I want to now break this down. And I want to break it down a little further. And so I want this product here to become addition, and I'm going to use my exponent rules as well. So the next line I'm going to show is actually going to have a couple of changes. And I'll say them as I go just so that you can see them. So this is going to become 2 times the natural log of x plus 1/3 times the natural log of 7x minus 14 minus 4 times the natural log of 1 plus x squared. And so on this line, I'm going to pause here for a second. On this line, what I've done is I've taken this product and I've separated it by the plus sign. I've also utilized the power rule for logs, and I've brought both of my exponents down in front. Okay, I've done the same thing here with this exponent. I've dropped it in front. And so now when I want to take the derivative of this, I can say, okay, let's take the derivative of this side, make that be more, the derivative of this side, and I want to take the derivative of this side. And so the derivative of natural log of y is 1 over y times y prime. Remember, chain rule. And then I want to come over here and I want to take the derivative of this. It becomes 2 over x plus the constant stays. And then it's the derivative of that thing, correct? Derivative of natural log times the derivative of the inside, which is just going to be 7, minus, now I have this one, the constant stays, 1 over 1 plus x squared, that's the derivative of the natural log of the quantity 1 plus x squared, times the derivative of the quantity, which is 2x. So notice in each case I have the derivative written, and so the natural log of x has a derivative 1 over x times the derivative of x, which is 1. We don't typically write that. It just is assumed that it's 1 and we don't multiply by 1. And so now we have 2 over x. I'm going to do two things on this step. I'm going to rewrite this as 7x minus 2, so I can cancel out those 7s. That's pretty nice. Plus 1 over 3 times the quantity x minus 2. And then I'm going to combine these two, and I get minus 8x over the quantity 1 plus x squared. And on this side, I have 1 over y times y prime. Remember, the goal is to get to y prime equals. That's the goal. So what I'm going to do here is I'm going to take y prime, leave it alone, and I'm going to take y times this quantity. This is a lot of work in this case, and it's okay, but we want to make sure we keep our work set clear and neat so that we can follow along. Okay, the last step now, I have a y here, and I can't have my derivative of y with respect to x in terms of a y. So now what I have to do is I have to come back up here. I'm going to scroll up so you can see. The original y way up here was this thing. So this right here is my original y. I now need to take that and I need to move it down so that it replaces what is the y in the bottom line that I currently have. Okay? So what I'm going to do right now is I'm going to take this that I have here in a green box, that's the y, and I'm going to now substitute it into my final step so that I can say, okay, now I have the derivative of y with respect to x. So this y from above is x squared times the cube root of 7x minus 14 all over 1 plus x squared to the 4th. And I'm multiplying that by the stuff that was already present here. 2 over x plus 3 over 3 times the quantity x minus 2 minus 8x over 1 plus x squared. I'm hoping I didn't make a simple error here in any point, because there's a lot of algebra, and it is likely that I dropped something or missed something. So please, 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 when you go back, double check this and make sure that I have not made an error, because it is highly likely. Okay, at this point, I'm going to box this answer, as that is the derivative. Now, in this case, I did not, I repeat, did not have to use logarithmic differentiation. However, it was a great method because I was able to simplify this really ugly mess, okay? Did I have to use logarithmic differentiation? Absolutely not. I could have just taken the derivative, used product property, quotient rule, and chain rule, and I would have been good, okay? It would have looked a little uglier to begin with, but it's all the same in the end, okay? Might be a nice little practice for you to try that on your own without using logarithmic differentiation and see how it works, okay? So a lot of work, but logarithmic differentiation actually makes it a little easier. Okay, here's where you're at now. You are now going to practice the quick check exercises. These are on page 195. You can go to page 196 to see the answers. If you are told to use logarithmic differentiation, for example, right here, that's going to look very, very similar to the last example that we just did, okay? So remember to use those log properties first, and then go back and take the derivatives, okay? Log properties first. It makes it easier. Okay, so page 195 for the quick check. Make sure if there were any questions in your note, especially on the last example, don't hesitate to ask tomorrow in class. All right, good luck.